All right, welcome everyone to this first video on chapter 17. We're going to talk about more types of equilibrium. A lot of it's going to be acid-base, as well as then some solubility product equilibria. So in this first video, we're just going to talk a little bit about some more kind of acid-base chemical reactions and some more things that can happen in solution when you mix different molecules, different compounds together. Okay. So we're going to revisit the idea of electrolytes. We talked about this earlier in the semester, right? First thing, right, we got to identify is there are strong and weak electrolytes. Now, before, we mainly just talked about strong electrolytes, things that 100% dissociated, 100% ionized, right? Strong electrolyte is like a strong acid or a strong base, right? They fully break apart in a solution, okay? Right? And so, an example here, this, fictitious molecule, CD2, right, will break apart into C2 plus 2D minus in solution, 100%, right? And that would be a strong electrolyte. Now, a weak electrolyte only breaks apart partially and establishes some type of equilibrium between the associated and dissociated version of the molecule, right? The things like weak acids and weak bases that we've talked about, okay? And so for for that example, right, the molecule CD, establishes an equilibrium with C plus and D plus or D minus in solution, right? Okay. And so, right, we've talked about, right, weak acids, weak bases, strong bases, and we've talked about how salts, right, can affect the pH of a solution, okay? And now we're going to talk a little bit more about how we, some more about calculating that pH and what is the pH of certain solutions when you add salts, as well as other things in the solution. Okay. So let's consider I have some sort of solution, right, that isn't, right, that I don't have just say pure water and I add some salt like sodium acetate, right? So let's pretend I'm adding sodium acetate to a solution, right? But instead of adding sodium acetate, right, NaCH3COO, right? So instead of adding just that to water, right, and saying, well, what is the pH? Okay, sodium acetate breaks up into sodium ions and acetate ions. Acetate ions establish an equilibrium, right, with the water to form acetic acid, OH minus, right, and that will affect the pH, and you can solve for that pH using ice tables, right? Let's now ask, right, what happens if we add this to a solution that already contains acetic acid, right? Well, if I have a solution that already contains acetic acid, right, so A here is equal to that CH3COO minus, right? Or I guess not the minus, but CH3COO, right? That's what that A is short for in this example, right, for the acetic acid. Okay, right, so if I already have this solution that contains acetic acid, right, that solution, right, has an equilibrium established, right, and then when I add that sodium acetate, okay, well, sodium acetate, right, is this Na, using the same notation as the equilibrium here, right, it's NaA, right, and that fully breaks apart to Na plus A minus, right, and we notice then that this A minus, it already exists in an equilibrium that's occurring in this solution, okay, and so this A minus, right, what we've done now is we've essentially kind of done an application of the LeChatelier's principle, right? We have this equilibrium that's established, and now we add some acetate ion to solution, and that is going to cause the equilibrium to shift to the left, right? And so I'm going to get less acetate ion and hydrogen ions in solution, right? Some of those are going to be consumed to form the acetic acid because of this LeChatelier's principle, right? LeChatelier's principle to reestablish the equilibrium, right? If I added some products, it's going to consume some of those products and form reactants, right? Which means I'm going to get less of my acid dissociated, right? in this solution, right? And then, as one would expect, right, adding a weak base to solution, right, it will raise the pH as well, right? Okay, and this effect is referred to as the common ion effect. Okay, and the common ion effect is whenever you have some sort of weak electrolyte and a strong electrolyte that contain a common ion in some type of an equilibrium reaction. When you mix those things together, what will happen is it will cause the weak electrolyte to ionize less than if it were alone in the solution, right? Because again, if I have some solution where I have HA, right, forming H plus A minus, right, and that establishes some equilibrium, and let's say it has like 5% dissociation, right? 5% of HA breaks apart into H plus and A minus, right? Well, if I add in, right, some amount of A minus by adding in, you know, sodium acetate, right? Again, in that example in the previous slide, right? Then that is going to cause this equilibrium to shift to the left, and then my percent ionization is going to go down to, say, like 3% or something like that, right? Where now the amount of HA that's broken apart is now only, say, 3% because of that common ion, right? So again, this is the common ion effect, right? That basically is saying that, you know, if you introduce some common ion to your equilibrium, right, according to Neutralization principle, it's going to cause the equilibrium to shift in the other direction of whether or not you added a reactant product, right, which will affect how much is broken apart and things of that nature, right? And we'll see this pop up again when we talk about solubility of salts in solution, okay? So if I have some problem related with this, right, okay, often what we'll need to do is we'll need to identify, okay, in this problem, hey, I have some weak and some strong electrolytes, and they have a common ion, right? Like that example of I had acetic acid and sodium acetate, right? I have this common ion, the acetate ion, right? And then what we'll do is we'll establish an equilibrium, right, for that weak electrolyte and fill up the ice table, right? But in that ice chart, we have to consider the fact that now from this strong electrolyte, we're going to have some initial concentration, right, of my other thing, right? So again, this HA, H plus A minus, right, equilibrium, right? I'm now going to have in this initial, I'm going to have some value here, right, and some value for A minus, right, and then I'll just have no, say, H plus initial, right, and then I go through and do my ice chart, right, from that starting point. Okay, so this common ion effect, right, will affect what is that initial concentration of some of the ions or some of the species involved in your weak electrolyte equilibrium. Okay, now, right, you need to make sure using concentrations, right, of the weak and strong electrolyte for those initial conditions as we're talking about, right, right, and again, make sure that in these charts you're using the molarity, okay, if you need to dilute the concentrations because you're mixing things, you know, then you have to consider that, okay, and then we often ignore spectator ions, right, those sodiums, potassiums, chlorides, you know, bromides, those types of ions, nitrates, right? Those ions are always spectator ions, right? Don't you know, aren't involved in any type of chemical reaction. Okay. And then one other chemical reaction that we're going to be talking about in this chapter is going to be acid-base neutralization reactions. Okay. So how these work, right, is typically in an acid-base neutralization reaction, you have some acid reacting with some base, okay? And note that these are not conjugate acid-base pairs, okay? So this acid and this base, right, are not conjugate acid-base pairs, okay? They are not conjugate acid pairs, right? So if I have a solution where I have acetic acid and acetate that I mix together, right? Those are conjugate acid-base pairs, so those don't undergo some type of acid-base neutralization reaction. Instead, that is a common ion effect problem, right? That has an equilibrium established, and I just am introducing ions on both sides of the equilibrium. Okay. Here, acid-base neutralization reactions are when you have an acid and a base that are different compounds, right? That they're like, an example here, hydrochloric acid and sodium hydroxide, right? Those are different acids, different bases, right? Those aren't conjugate acid-base pairs. Those will react with each other to form a salt, okay, plus water, right? HOH here, that's H2O, right? And I wrote it in that way because, right, because you can see, right, effectively what's going on is you're swapping the cations, you know, between the two species, or swapping anions, however you want to view it, right? Right, the net ionic equation for this reaction is just hydrogen ions plus hydroxide ions forming water, right? And this is the net equation when you have a strong acid and a strong base being added together, okay? And it's not always the case if you have weak acids and weak bases and things like that, but, okay, right? Now, if you have a reaction involving something like ammonia, right, where you have, again, your base here and your acid here, right, it still does form a salt, but in this case, there is no water, right? Because your base doesn't have hydroxide, your base is a proton acceptor, and that proton acceptor isn't hydroxide, so and so that won't form water, okay, but it'll still form a salt, right? So these acid-base reactions will still form salt, but again, right, we're going to have a lot of examples, a lot of different things where we mix together different stuff in solution, right? If I add an acid and a base into solution, right, if they're conjugate acid-base pairs, then it'll be kind of these common ion effect problems. But if they're not conjugate acid-base pairs, then they will undergo a chemical reaction like what's described here.